Hello to everyone, this is Shantan Kumar, Assistant Professor, Department of Mathematics, Institute of Aeronautical Engineering College, Dundigal, Hyderabad. Subject is matrices and calculus. Today, we are going to discuss the topic on Cayley-Hamilton theorem problems and also based upon the theorem, that is application. Before going to discuss the Cayley-Hamilton theorem problems and also applications, here these are the based upon the totally, that is finding the characteristic equation and finding the eigenvalues, and based upon that we need to find out according to one by one, that is a verification of the theorem and as well as the applications of the Cayley-Hamilton theorem. First of all, in this lecture we are going to discuss the characteristic equations and also the eigenvalues. In previous sessions we discussed clearly how to find the eigenvalues and how to find the eigenvectors, and again before that, how to find the characteristic equations. That means, by using the characteristic equation, how to find the eigenvalues and how to find the eigenvectors. That clearly we discussed in the previous two lectures. And today, we are going to discuss based upon the characteristic equation, that is a Cayley-Hamilton theorem, the verification as well as the applications of the Cayley-Hamilton theorem. Here, first of all, what is a characteristic equation? That means, how to define the characteristic equation. And today also we need to discuss some little bit about that regarding the characteristic equation and also finding the eigenvalues if possible. See, what is the characteristic equations? That means, for example, if it is assumed that is a 3 by 3 in a square matrix, like according to here, A11, A12, A13, A21, A22, A23, and again A31, A32, A33, be a square matrix of order 3 by 3. And also, we need to assume the corresponding unit matrix of order 3, that is I is equal to 1, 0, 0, 0, 1, 0, 0, 0, 1, be an identity matrix. And also, if it is considered, we need to assume that lambda be a scalar. And with the help of this A and I and also that lambda, with the help of these three together, you need to consider what is the box of A minus lambda I. That means matrix notation A minus lambda I. This matrix A minus lambda is called, that is a characteristic matrix. That means with the help of the A comma lambda comma I, we need to find out that is A minus lambda I, that we obtain very clearly matrix notation only. That is a characteristic matrix. And based upon this one, we need to find out what is a characteristic polynomial. The characteristic polynomial is nothing but whatever we found it, that is a characteristic matrix. And we need to find out the data of A minus lambda I. That means it is obtain the equation, not equation, it is a polynomial terminology. That is a characteristic polynomial. And with the help of this characteristic polynomial, again we need to find the equate that 0. That means data of A minus lambda I is equal to 0 is called the characteristic equation. These are the one by one interlinked with that matrix from the matrix. One is the characteristic matrix and characteristic polynomial and also characteristic equation. And by using these are the characteristic equation, while we are going to solving that, we get the values. That values are called the characteristic values or eigenvalues or proper values or latent values. And now we'll go to discuss here how to find. That means under the 2 by 2 and also the 3 by 3, by using the characteristic equation, how to get that standard equation. That we need to discuss here clearly. And before that, again we need to one example suitable with the three definitions. That is a characteristic matrix, characteristic polynomial, characteristic equation. And whatever we understood the previous slide, that is a matrix. That means here let A be a square matrix of order n. Then the matrix, that is a box of, that is a matrix of A minus lambda I is called the characteristic matrix. For example, if it is a consider here I is also unit matrix and again lambda is a scalar. And with the help of that A comma I comma A lambda, and for example, you need to assume here it is a 2 by 2 simple example, that A is a matrix, that is a 1 minus 2, 4 and also 1. And with the help of this box of A minus lambda, that means in the diagonal element subtraction with lambda, that means 1 minus lambda minus 2 and 4 and again 1 minus lambda. This is clearly we obtain in the matrix notation. That means characteristic matrix of A is a given matrix and characteristic it is a polynomial. The characteristic polynomial is nothing but here whatever we obtain it is a characteristic matrix. Then we need to find out in the polynomial. That means by using the data of A minus lambda. That means the data of A minus lambda is called that is a characteristic polynomial. And same, for example, we need to assume the matrix. Example, it is A is a matrix 1 minus 2 and 4 and 1. And it is a data of A minus lambda. Here data of A minus lambda is a whatever you obtain that is a matrix. If you need to find out that is a det. That means as we know that AD minus BC, therefore with the help of the AD minus BC, we form the polynomial term. That here after the simplification we obtain clearly lambda square plus 2 lambda plus 9. This is we obtain that in the polynomial. Therefore, it is called the characteristic polynomial of the matrix A. And similarly further we need to find the equation with same the example. That means here is that is a data of A minus lambda is equal to 0. That means while we are going to finding same the equation lambda square minus 2 lambda plus 9, that equation is equating the 0. That means here the data of A minus lambda is equal to 0 is called the characteristic equation of the given matrix. And here also let us assume the matrix A, it is the same matrix and the polynomial is also same the polynomial. This polynomial equate the 0. Then it is called as a characteristic equations. Therefore, these are the with the example here for the purpose of that is a characteristic matrix and characteristic polynomial and characteristic equation of the matrix A is the condition. And further we need to discuss here according to the Cayley theorem. That means here with the help of the characteristic equation in previous lectures we discussed clearly the eigenvalues and again like vectors that corresponding the eigenvalues and briefly we discussed in the previous sessions. And today's sessions we need to discuss based upon this characteristic equation here what is the Cayley-Hamilton theorem and again based upon the Cayley-Hamilton theorem what are the applications like what are the methods we need to find out by using the Cayley-Hamilton. Here, first of all, here under the characteristic equation that is 2 by 2, like for example, these are the like standard equations like what is the equation you obtain in the by using the characteristic equation that we need to discuss. Here, for example, 2 by 2 matrix. As we know that 2 by 2 matrix that is for example, A11, A12 and A21, A22. And under the 2 by 2 by using the characteristic equation. That means we know that the data of A minus lambda is equal to 0. The data of A minus lambda is equal to 0 means as we know that according to that subtraction with minus lambda in the diagonal elements, then you find the AD minus BC. And here while that is like essay like discussion is like in different way, that is simplification is taking the time. But here shortly we need to find out with the help of the short method. That short method is nothing but under the 2 by 2 the characteristic equation is lambda square minus S1 lambda plus S2 is equal to 0. That where it is a S1, that S1 is nothing but it is the sum of the diagonal elements. And diagonal elements means as we know the given matrix what are the principal diagonal elements. And again that is a cross of the determinant values of the matrix. And again here that is nothing but it is a sum trace of the matrix are also sometimes. That means the trace of the matrix is nothing but sum of the that is a diagonal elements. And S2 is nothing but the determinant of the matrix. But here clearly it is mentioned that directly it is the det. That means sometimes it is also denoted S2. Therefore, under the 2 by 2 any matrix is given, we need to find out that is a lambda square minus S1 lambda plus S2 is equal to 0, where that S1 is nothing but it is a trace of the matrix and S2 is nothing but the data of the matrix. And further, for example, the 3 by 3. That means here given that example is A11, A12, A13 and A21, A22, A23 and A31, A32, A33. And based upon it, we need to require in the third order polynomial. Because of the matrix is given the 2 by 2 that we obtain that is a second order polynomial. Whereas the given matrix is the 3 by 3 order, we need to find out that is a third order polynomial. And under the third order polynomial, we get by using the characteristic equation is in generally, that means shortly, that is a lambda cube minus s1 lambda square and plus s2 lambda minus s3 is equal to 0. And here also, the s1 means same under the 2 by 2. It is also trace of the matrix. That means the sum of the diagonal elements. And under the s2, that is the sum of the minus of the diagonal elements. That means sum of the minus of the diagonal elements. For example, the matrix is a 3 by 3. Then we need to find out the diagonal elements are the 3. The 3 particular values we need to find out what is the minus of the values, and we need to find out the sum also. That is the meaning of the sum of the minus of the diagonal elements. And similarly, and again that S3. That S3 is nothing but the determinant of the given matrix. But here clearly given it is a muddet A, that is nothing but it is a S3 is a condition. That means under these are the short methods we need to discuss. Then easy to find out what is the characteristic equation with the help of under that 2 by 2 and also 3 by 3 matrix. For example, we need to discuss here what is the Cayley-Hamilton theorem. First of all, we need to understand what is the Cayley-Hamilton statement. Here, it is not required the verification of the theorem. That is, a proof of the theorem is not required. We need to discuss what is the statement of the Cayley-Hamilton theorem and also what are the applications of the Cayley-Hamilton theorem. For example, the Cayley-Hamilton theorem. And based upon this theorem, the two applications are here arranged. And one is to finding the powers of the matrix, and second one is to finding the inverse of the matrix. That means based upon that, by using the Cayley-Hamilton theorem, the two applications, one is either the find the inverse and also that is powers of the matrix. That means these are the two conditions to find out by using the Cayley-Hamilton theorem, that is the applications. And here that means we should not find out the powers is nothing but directly from the matrix. By using the Cayley-Hamilton theorem, we need to find the powers as well as the inverse of the matrix. And here also the inverse is nothing but it is not finding by using that either the Gauss-Jordan or something adjacent of A by A, det A. That we are not going to discuss the methods. It is by using the Cayley-Hamilton theorem, we need to find out the powers and also the inverse of the matrix. Here. Now, what is the statement of the Cayley-Hamilton theorem? That means how to verify the Cayley-Hamilton theorem from any given matrix. That means we need to understand what is the statement of the Cayley-Hamilton theorem. That means the procedure to find the Cayley-Hamilton theorem, whatever it may be, first we need to understand that is the statement of the Cayley-Hamilton theorem. That means every square matrix satisfies its own characteristic equation. That is the meaning of here. Every square matrix satisfies its own characteristic equations. And we need to understand the statement clearly, what is the meaning of this. That means under this statement, we need to find out first is a characteristic equation. And after that, we need to satisfy the given matrix, the equations related. That means, for example, from the matrix, we need to find the characteristic equation. And the characteristic equation means we obtain under the lambda. And that lambda is satisfied the given matrix. That is the meaning of here. It is a one matrix is a given matrix. That is the meaning of every square matrix satisfies its own characteristic equation. And if you understand properly the meaning of the statement, the verification is easy to get the verification. And for example, what is a working rule under this is the 2 by 2. That means based upon the statement, how to verify from the given matrix 2 by 2 is the order of the matrix. What is the working rule? And here the procedure of the working rule under, first we need to find the characteristic equation of the given. That means we need to find the characteristic equation. As we know that the characteristic equation is nothing but it is the delta of A minus lambda I is equal to 0. That is the meaning of the characteristic equation. And in this, we need to replace lambda is equal to A. That means whatever it is the equation in this, and in this equation, we need to replace in here lambda is equal to A. In this, the characteristic equation. And that characteristic equation is considered, it is like star. That means our choice, sometimes it is a one equation or A equation, whatever maybe. That equation is treated as we give that some number. and here either the number or any notations. And again, based upon this one, here further, for example, under the 2 by 2, that means we obtain the lambda equation in terms of that is a square and also a comma like that values. And a, as we know that a is equal to the given matrix only, and here a square, that values we don't know that. Therefore, here we need to find out what is the a square from the given matrix. That a square is nothing but, again we know that according to it is a square is equal to a into that is a. We need to find out a square into that is a square is equal to a into a. And after that, getting that a square, again we need to replace whatever it is a consider equation that is a star or whatever it may be. In that we need to replace a square and a and also the value of that I. By using all these values, you need to replace in the star equation, and therefore the equation will be get the values is equal to 0. That is the meaning of verification of the Cayley-Hamilton theorem. And also, if you want to find the application, that means under the applications, as we know that A inverse and again the powers of the matrix. For example, one of the operations, if you are going to find in the A inverse, then we need to, whatever we obtain that is the equation of A, that equation is multiplication with on both sides, that is A inverse. That is the meaning of, if you want to find the A inverse, that multiplication, the star equation is on both sides, it is A square. Then we can find the value of inverse of the matrix. And while we are going to discuss the problem also easy to understand, but this procedure we need to understand the clear concept only. And this is the procedure to verification of the Cayley-Hamilton theorem and find the inverse of the matrix under the 2 by 2 matrix. And similarly, for example, that is a 3 by 3 for example. That means every square matrix satisfies its own characteristic equation. For example, it is a 2 by 2, one problem we need to discuss. And here the problem is nothing but it is a, for the matrix A is equal to 1, 3, 4, 5. And again, we need to, it is its characteristic equation is lambda square minus 6 lambda minus 7 is equal to 0. Because of, as we know that according to the data of A minus lambda I is equal to, that is equation is lambda square minus s1 lambda plus s2 is equal to 0. That s1 is nothing but it is a trace is 1 plus 5 is equal to that is 2. And s2 is nothing but the data of that 1, 3, 4, 5. The value is equal to clearly, it is a minus 7. And based upon this one, because of 5 minus 12 is equal to minus 7. And based upon this one, we can replace in the equation. We obtain that characteristic equation. Regarding this one, in the previous lectures, we clearly discussed that how to find the characteristic equation in a proper manner. And again further, now here, according to the characteristic equation, this one, here we need to verify the Cayley-Hamilton theorem. That means here, according to the procedure, after getting the characteristic equation, we need to replace that lambda is equal to, that is a is a matrix. And from here, the characteristic equation from here, we need to replace lambda is equal to A. That means we obtain that A square, it is A square minus 6A minus 7. That 7 is nothing but 7 into I is equal to 0 because of the constant is multiplication with the unit matrix. There is no change. Therefore, it is a minus 7I is equal to, we need to verify 0. If it is satisfied is equal to 0, then verification of the Cayley-Hamilton theorem is completed. And now our target is under this one, it is A square is required because of we don't know the value of A square, but we know that only A. Therefore, from this given matrix A, we need to find out what is A square. That A square is equal to nothing but, here finding that A square is nothing but A into A. Therefore, A is the 1, 3, 4, 5. And one more A is the 1, 3 and 4, 5. The matrix is clearly 13 and 18 and 24 and again 37. And this matrix can be replaced in the characteristic equation after getting replacing that lambda is equal to A. And again, minus 6 into A. That A is as we know that is a given matrix. Therefore, minus 6 into A is nothing but here after that multiplication with 6, the given matrix. Therefore, 6, 18 and again 24 and again 30 and again minus 7I. That means I is know that unit matrix of order 2, that is 1001. Multiplication with 7, that is 7007 is a matrix. And further, we need to addition of that 13 minus 7 is like that 7, and 7 minus 7 is also 0, and 18 minus 18 minus 0 is also nothing but 0. And finally, that corresponding elements we need to addition and subtraction. The value output will be, it is a 0000 is the value, and it is equal 0 is nothing but is equal totally, that is a 0 is a value. Therefore, the meaning of that a square minus 6a minus 6a and again minus 7i is equal to 0 is nothing but it is a verification of the Cayley-Hamilton theorem is successfully completed. And this is a simple example for our understanding. The given matrix is the like a 2 by 2 matrix. Here, how to verify the Cayley-Hamilton theorem. Here, for example, verify the Cayley-Hamilton theorem for the matrix is 1 minus 1, 2 and also 3. The matrix. That means we need to verify the Cayley-Hamilton theorem for A is equal to 1 minus 1, 2, 3 is a value. And we need to find out first what is it according to the statement of the Cayley-Hamilton theorem. We need to find out what is a characteristic equation. That means as we know that the characteristic equation is nothing but delta of A minus lambda is equal to 0. That is, delta of A minus lambda is equal to 0 is nothing but then shortly we obtain the equation is lambda square minus s1 lambda plus s2 is equal to 0. Because of this matrix is the 2 by 2 matrix. Therefore, we obtain that required the lambda square minus s1 lambda plus s2 is equal to 0. And here we don't know that here, and again as per the characteristic equation we should be satisfied the given matrix. That is the meaning of according to the Cayley-Hamilton theorem. We need to replace after getting the like characteristic equation at lambda is equal to A. And here first we need to find out what is a S1. Here S1 is nothing but as you know that there is a trace of the matrix, and under the trace of the matrix here the trace is nothing but 1 plus 3. Therefore, S1 is nothing but it is a value sir 1 plus 3 is equal to 4 is a value. And S2, that S2 is nothing but based upon the data of the matrix. And here the data is nothing but 1 into 3 is a 3 minus of minus 1 into that is a 2. Therefore, that S2 is nothing but the data of the matrix is 3 plus 2 is equal to it is a 5. Therefore, it is a S1 is over and S2 is also over. That value here replaced in the equation 1. Therefore, the characteristic equation is reduced to like that lambda square minus 4 lambda plus 5 is equal to 0. This is the meaning of according to that characteristic equation clearly we completed. Now, our target is to verify the Cayley-Hamilton theorem. That means whatever we obtain the characteristic equation, we need to replace lambda is equal to A is the value. Therefore, further we need to replace lambda is equal to A is the matrix. Therefore, after replacing lambda is equal to A, the matrix is reduced to like A square minus 4A plus 5 into 1. That 5 into AI is equal to 0. And here we need to show that is equal to 0. And again, here if you want to verify is equal to 0, here it is required I. That we know that I is a unit matrix of order 2, that is 1001, and A is the given matrix. Here the given matrix is 1 minus 1, 2 and 3. And again the A square, that we need to find out here the A square. That A square is nothing but highest is in the previous example that A into A. Therefore, A into A is nothing but A is a given matrix and again A. That is a 1 minus 1, 2, 3 and 1 minus 1, 2, 3. The product of these two, that is A into A square, the value is clearly minus 1, minus 4 and 8 and also 7 value. And here by using this A square and here given matrix A and also I, we need to replace in the equation 1. The equation 1 is nothing but our equation 2 what will be. And again the equation is reduced to like that. It is from the equation 2, that is A square. That is A square is a here just now completed is a minus 1, minus 4, 8, 7. And A is a given matrix. And again I, that I is nothing but it is a unit matrix of order. That is a corresponding the order is a 1001. Therefore, I is nothing but 5 into I is a here after that simplification that is a 5. That is a 5005. And now we need to adding and subtraction with the help of the three matrices. Here minus 1, minus 4 and 5. Therefore, the first element should be 0. And again, the second one, minus 4 plus 4 plus 0, the value is also 0. And similarly, third element and fourth element is also reduced to 0. Therefore, the meaning of it is clearly showing that 0, 0, 0, 0. And the meaning of this one, it is equal to 0 is finally the verified the Cayley-Hamilton theorem. Because of, we need to verify after getting the characteristic equation and replacing lambda is equal to a, it should be satisfied is equal to 0. Therefore, it is a meaning of verified the Cayley-Hamilton theorem. And now, again, we need to discuss one more, that Cayley-Hamilton theorem, and also find the inverse. That means in this problem, not only to find the verifications and including the using the using the Cayley-Hamilton theorem. Here they are asking to find the value only. That means in this problem, they are not asking to verify the Cayley-Hamilton theorem, but they are asking to find out by using the Cayley-Hamilton theorem, need to find out only inverse of the matrix. That how to find out, that we need to discuss properly. That is the meaning of application of the problem. And again here, but without understanding this one, you should not do that. A inverse is nothing but either the Gauss-Jordan or some inverse of like urgent of a bed day. That we are not going to finding. And anyhow, using the Cayley-Hamilton theorem, that means according to the Cayley-Hamilton theorem is nothing but we need to require compulsory, it is a characteristic equation. The characteristic equation of the matrix of A is equal to lambda square minus S1 lambda plus S2 is equal to 0. And again, as we know that S1 is a trace of the matrix, that is S1 is nothing but it is a 4. And S2 is nothing but the matrix is a 3 plus 2 is equal to, that is also 5. And again here, that is putting these values in the equation 1, the matrix is reduced to lambda square minus 4 lambda plus 5 is equal to 0. And after getting this one, here by the Cayley-Hamilton theorem, we should not verify this the Cayley-Hamilton theorem. The problem is by using the Cayley-Hamilton theorem. And as per the concept of the Cayley-Hamilton theorem, the characteristic equation is satisfied the given matrix. Therefore, first, by the theorem, we need to replace lambda is equal to a. Therefore, a square minus 4a plus 5a is equal to 0. This is by the theorem, it should be satisfied the characteristic equations. We should not verify this is the problem. And but here, by using these equations, we need to find out the application part is A inverse. As per the working rule of the A inverse, according to as we know that, it is multiplied with the A inverse in the equation of that A square, this is the equation. Therefore, we need to multiply A inverse on both sides of the above equation. Therefore, after multiplication A inverse, that first one is A into A inverse into A square minus 4 into A into A inverse plus 5A into A, that is A inverse, the right side A inverse into 0. And while we are going to observing here, as we know that the meaning of A inverse into A square is A, and A into A inverse is I, and I into A inverse is A inverse, the right should it be, that is a 0. And based upon this one, the equation is reduced to like according to, it is A minus 4I plus 5A inverse is equal to 0. And from this equation, as per the concept, we need to find out what is the inverse. Therefore, the inverse is nothing but it is existed 5A inverse. Therefore, if it is treated as 5A inverse is equal to, that is a 4I minus A is the value. That means LHS terms it right the right side, that is a 4I minus A is the value. And further, we need to find out A inverse. Therefore, A inverse is nothing but it is 1 by 5 of 4I minus A. That values we need to find out what is the 4I minus A is the value. And I, as we know that I is equal to 1001 and A is equal to, that is a given matrix. Therefore, by using the unit matrix and by using the given matrix, the matrix is reduced like that 4I minus A is the value. It is a 4I minus A is the value. And here 4 minus 1, that is a 3, and 0 minus or minus 1 is that is 1, and 0 minus 2 is a minus 2, and 4 minus 3 is equal to 1. Therefore, after that simplification of in between the values, that A inverse is equal to 1 by 5 into, that is a 3, 1 minus 2, that is a 1 value. Therefore, this is the required equation of the inverse from the given matrix by using the Cayley-Hamilton theorem. That is meaning of this is a clear procedure to find the inverse of the matrix by using the Cayley-Hamilton theorem. For example, now up to here it is a 2 by 2 matrix, that is a verification the Cayley-Hamilton theorem, and find the inverse of the matrix. Now further we need to discuss under the 3 by 3 matrix. Under the 3 by 3, same as it is under the 2 by 2, whatever we understood that A inverse, that is a power 4 like A square, and again by using the Cayley-Hamilton theorem, and here also the procedure is that 3 by 3 is also like that. First, according to the statement, every square matrix satisfies its own characteristic equation, and next we need to find out what is the characteristic equation, and further we need to put lambda is equal to A. But here this is the matrix is a 3 by 3. Therefore, we need to find out not only A square, including the A cube is also required. The A cube, A square is nothing but A into A, and A cube is nothing but it is a square into A. That means whatever we obtain, that is a 1 by 1 values. Therefore, here by finding that A cube and A and also A square, then we need to replace in the whatever you treated as the equation 1, that we need to replace. And again, after verification this one, if we need to find out that is A inverse, we should be multiplying same in the previous problem under the 2 by 2 process. We need to multiply A inverse on both sides. For example, we need to discuss find the Cayley-Hamilton theorem and find the inverse of the matrix. That means the matrix we need to find out. First, the characteristic equation is required. As we know that how to find the characteristic equation. That means with the help of the delta of A minus lambda is equal to 0. Therefore, the delta of A minus lambda is equal to, here under the 3 by 3, the equation is shortly method lambda cube minus s1 lambda square plus s2 lambda minus s3 is equal to 0. This is also regarding in the previous sessions we discussed clearly here how to get 1 by 1. And again here also the meaning of s1 is the trace of the matrix, and again the s2 is the sum of the minus of the diagonal, and s3 is the delta of the matrix. And based upon like s1, s2, s3, we need to find out. For example, first one, s1, the trace of A, and in this matrix trace is nothing but 2 plus 2 plus 2, the value is 6, and s2, the sum of the minus of the diagonal elements. Therefore, the diagonal elements, first one is the 2 is the, that is 2 minus 1, it is the first minor element, and second minor element, that is also the second one. That means in the previous lectures we discussed clearly how to find the minus, clearly we shown in the animated, then how to find the solutions. Right? S3, that S3 is also nothing but, that means we need to find out first element minor and second minor and also third minor. That is the meaning of these are the 3 values. After deleting that particular row and column, we obtain like this. And again, next we need to find out the det value, and after that sum. That means sum of the values. And after finding that 2 by 2, as we know that according to AD minus BC, the values are clearly we obtain. That is 3 plus 3 plus 3. Therefore, S2 is equal to, the value is nothing but it is a 9 value. And here further it is required S3. That S3 is nothing but the determinant of the matrix. The determinant of the matrix is nothing but, as we know that how to find the data of the values. The value is clearly, it is equal to, according to the simplification, the value is 4. That means S1 is a trace and S2 is the 9 and S3 is equal to 4. These values we can replace in the star or equation 1, whatever we obtain in the A terminology. Therefore, that is we obtain the lambda square, lambda cube minus, it is a trace in nothing but it is a 6 lambda square plus 9 lambda minus 4 is equal to 0. And this equation is satisfied according to the Cayley-Hamilton theorem. That means we need to replace lambda is equal to A. After replacement of like lambda is equal to A by using the Cayley-Hamilton theorem, here according to the equation is reduced to A square, A cube minus 6A square plus 9A minus 4 into I is equal to 0, because the 4 is a constant which we need to reduce to 0. That means we need to verify here this one. Here how to verify this one? That means in this I means, as we know that is a 3 by 3 is a given matrix. Therefore, the 3 by 3, the unit matrix of order, that is a 1 0 0 0 1 0 and 0 0 1. And A, the A is nothing but the given matrix, and we need to find out A square. The A square, as we know that from the matrix A, we need to find out what is A into A. And further, we need to find out what is A cube. That A cube is also nothing but A square into A is a matrix. That means already we found that A square, that values you can replace, find the value. Therefore, by solving that, it is A square, that A is a given matrix and A is the matrix of this one. By the product of this one, we obtain these are the matrices. This is the matrix. Therefore, by using these values, and again, further, we need to proceed in A cube. And A cube is nothing but, as you know, that A square and A. And A square, already we are completed A square. That value we can replace here A square. And A, that A is nothing but the given matrix. And the product of A square and A, that means accordingly we obtain the required A cube, this is the value. And after getting this the A cube and A square and also given matrix and the corresponding the unit matrix, then we need to replace in the whatever the verifications. Therefore, after replacement of one by one, that A cube and A square and A and also I, the matrix is like A cube is this one, that we can replace here. And A square, already we completed that A square also, that also we need to replace here. And again, after multiplication with 6, and again, plus 9A. That means A is, we know that this A is multiplication with 9. The matrix is reduced to like that 9A. And further, it is I is multiplied with 4. That I is also the suitable matrix of the unit matrix. This is the 3 by 3 unit matrix. This value we can multiply with 4. Therefore, the matrix is a 4A is like this. And again, after that individually, that is a first element, and first element, the value should be clearly, it is a 0. And corresponding the second one, including the plus and minus, the value is 0. And similarly, the third element, and again, similarly, rest of the all elements, while we are going to addition and subtraction, the value should be clearly, that is 0, 0, 0, 0, 0, 0, and 0, 0, 0. That means it is a null matrix. That means it is equal to total is 0. And if it is equal to 0 means that is a equation is satisfied. It is a Cayley-Hamilton theorem is a verified. Hence, it is a meaning of that is a verified the Cayley-Hamilton theorem. That means it is satisfied the characteristic equation of the given matrix A. And further, here we need to find out what is the inverse of the matrix. The inverse of the matrix is nothing but whatever we equation of the, like according to this equation, we should be multiplying according to as per the application, it is multiplied with A inverse. Therefore, here to find the A inverse, whatever the equation like according to here, this equation is multiplication on both sides with A inverse. Therefore, while we are multiplied with the A inverse, the matrix is reduced to like this. Now again further, that A inverse into A cube minus A inverse into that is a 6 into A square. And again after that multiplication, A cube, A inverse into A cube is A square. And A inverse into A square is A, and A inverse into A is I, and A inverse into I is nothing but A inverse. The right side should be 0. But our target is, we need to find out that is a inverse. That means that we can consider that is a 4A inverse is equal to, if it is considered the right side, the equation is like this. And again further, we need to find out A inverse only. Therefore, A inverse is equal to 1 by 4 into A square minus 4A plus 9A is a value. And again further, we need to find out what is A square and A and also I. Already we completed A square and A, as we know that I is also, you know that. By using that I and A is a given matrix and A square, that we need to replace in the 1 by 4 of the matrix. Therefore 1 by 4, that A square. As we know that the A inverse is the A square is like this, and A, and again multiplied with 6, therefore minus into 6 into A is this one, and plus 9I, that I is multiplied with unit matrix. The matrix is the 900, 090 and 009. And once again we need to simplify 6 minus 12 and again plus 9 and minus 9 and again plus 6 and again plus 0, 5 minus, like these are the values. While we are going to addition and subtraction the corresponding elements, the inverse is equal to, we obtain that clearly 1 by 4 into these are the particular values. That means it is the first element, second, third, and also third value. And according to all the rest of the values, we need to find out like this. Therefore, A inverse is equal to 1 by 4 into the matrix is like this. This is the required matrix of the inverse of the required matrix by using the Cayley-Hamilton theorem. Hence, it is completed the inverse of the matrix by using the Cayley-Hamilton theorem. And for example, same, this is also under the Cayley-Hamilton theorem verify that. But in this problem, they are not asking to find the inverse. Here we need to ask like that, find the a power 4. That means it is also one other applications by using the Cayley-Hamilton theorem. And previous problem is other application to find the inverse of the matrix. Now here how to find the like a power 4 by using this one. And while we are going to discuss this one, for example, first of all require the Cayley equation. And as we know that lambda q minus s1 lambda square plus s2 lambda minus s3 is equal to 0. And again, as we know that s1 is the trace of the matrix. And again, s2 is the, here s1 is the 3. And again, s3, 2 is the sum of the minors of the diagonal elements. Therefore, the sum of the minors means first minor is like 1 1 3 1 and second minor is like according to the first minor, and second minor is this one, and the third minor is 1 1 3 1, and this we need to addition like with the help of the middle of the term, that is a plus plus plus. The value is s2 is equal to, clearly we obtain the values are minus 7. And further we need to find out what is the s3. That is, as you know that is a data of the matrix is equal to 11 is the final solutions. Now again we need to replace in the equation 1, whatever we assume that is a lambda q minus s1 lambda square plus s2 lambda minus s3 is equal to 0. Now we completed s1 and s2 and s3. These are the equations. As per the Cayley-Hamilton theorem, we should be satisfied the given matrix is satisfied the characteristic equation. That means we need to replace lambda is equal to a. Therefore, we need to get that is a cube minus 3a square minus a1a minus 11 into I, because of it is a constant. Therefore, minus 11 into I is equal to 0. And here to verify, that means a square into, it is required a cube, that means a square into a cube, a square is required, and as we know that, and this one here, a square is equal to a into a. A is a given matrix and a matrix, we obtain this is a square. And a cube is a square into a. And a square is equal to, we know that already completed above the a square, and a the given matrix, and a cube by multiplication of this a square into a, you obtain this matrix. And now the rest of the values we know that I and also a is a matrix. Therefore, by using this a square and also a cube, we need to replace in the equation of this one. A cube and again a square and again a the given matrix I, that is a unit matrix, is multiplied with 11. Now again first element, first element, first element, first, second, 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 third, 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 and also third one. Therefore, by using addition and subtraction, rest of all the values are same like this, we obtain is equal to 0 0 0. That means it is a null matrix. That means total the value is 0. Therefore, the equation is a cube minus 3a square minus 7a minus 11a is equal to 0. That is the meaning of verified the Cayley-Hamilton theorem. And further, we need to find out what is the applications to find the a power 4. That means at the time of that finding that a power 4, here in the whatever the equation you obtain that second equation, here whereas the inverse we need to multiply, that equation is multiplication with the inverse, but here it is required that a power 4. Therefore, we need to multiply with the same second equation by a is the value. That means this equation is multiplication with a. That means it is a power 4 is equal to, therefore the right side is a 3a cube plus 7a square plus 11a. And here a cube already completed, a square already completed, a the given matrix. That matrices are replaced. That a cube is this one already completed. This value is multiplication with 3 value. The matrix is reduced to this one. And plus a square. A square we know that is multiplied with 7. Therefore, the matrix is reduced like this. And 11a. Again we know that a is the matrix, given matrix, multiplied with 11. Therefore, the matrix is reduced to like this. And further, we need to addition first one, second one, fourth one, second one, second one, second one, and third one, and third one. Like according to all the corresponding values, we need to addition individually. Sometimes it is based upon the subtraction, that whatever the obtain the values. And here the successful, all the values are a power 4 is equal to, this is the matrix is a power 4 is equal to, this is a clear matrix. That means these are the clear, the procedure to find the verification of the Cayley-Hamilton theorem and also the applications of under the Cayley-Hamilton theorem. One problem is clearly we discussed, that is the inverse, and another, this problem is based upon the powers of the matrix. These are the two are the under the Cayley-Hamilton theorem two applications. And for example, under same, this is also here verify the Cayley-Hamilton theorem and find the inverse of the matrix. Same in the according to the previous one example to find the conditions. First, any problem is given, like inverse is nothing but same here also the Cayley-Hamilton theorem and find the inverse. Same we need to verify after finding that like S1, S2, S3, the inverse is also here in these equations. We need to replace lambda is equal to A also. We need to verify. We obtain it is inverse. These are the some problems for practicing the problems based on the Cayley-Hamilton theorem, like to finding the inverse and also the powers of the matrix under the application problems. Same here also other example. Do evaluate. Here also we need to verify that lambda is equal to A. The equation is we need to prove that A cube minus 4A square plus 4A plus 4 into I, that is it is I is equal to 0. And A inverse is equal to, that equation is multiplication with A inverse. Then you get the values. And A power 4. Verify the Cayley-Hamilton theorem and A power 4. The characteristic equations is like this. And S1 is to S3. Here S1 is the trace and S2 is the sum of the minus and S3 is the determinant of the matrix. Now we need to prove that by replacement of lambda is equal to A, that is the matrix is A cube minus 5A square plus 7A minus 3I is equal to 0, and we need to verify. And after that again A power 4, that means which is multiplied with 2, that is A is a matrix. Then we obtain in terms of A power 4, and again we need to find out that we obtain the clear values. And it is some different type of the problem based upon the Cayley-Hamilton theorem. And while we are going to observing using the Cayley-Hamilton theorem, means we need to find out what is a characteristic equation. That means under the 2 by 2, as we know that the characteristic equation, and lambda is equal to, we should not verify that they are asking to using the Cayley-Hamilton theorem, means as per the Cayley-Hamilton theorem we need to replace lambda is equal to A. Therefore lambda is equal to A means A square minus 5 S1 lambda minus S2 like that values, and S1 is a trace. The trace is nothing but 0. S2 is equal to minus 5. Therefore from the equation 1, lambda square minus 0 lambda minus 5 is equal to 0. Therefore A square is equal to minus 5. And by using this one, where whatever we discussed in the previous lectures, that is the previous problems, it is finding the inverse and finding the powers of the matrix. And it is also powers of the matrix, but it is some logically problem. Whatever we obtain, this is the characteristic equation, that is a Cayley-Hamilton theorem, it should be satisfied the problem. Therefore by using this one, A square is equal to, that is a value is a 5i. A square is equal to 5 here. By using this one, we need to find out, that is A 4 8 is equal to 625i. Then how to find out this one? That means here, while we are going to finding that it is A 4 8, for example, A 4 8 is treated as A square into I. That A 4 8 is equal to 5A square, because of, as we know, we required, it is finding that given, already we know that it is A square minus 5i is equal to 0. It is A square is equal to 5i. That means it is A power 8 means we need to multiplying that A power 6 is the value, that both sides. Therefore A power 8 is equal to 5 into A power 6. And again A power 6, that we treated as A square into A square into A square. Therefore it is A square. Once again A square is equal to, we know that it is a replacement of 5i 5i 5i. That means the solution it will be clearly the LHS side is a power 8 and right side is a 625 into I is the value. Therefore, it is somewhat different problem under the Cayley-Hamilton theorem by using the characteristic equations. For example, this one. While we are going to observing here also something different type of the problem here, find the determine the A inverse by using the Cayley-Hamilton theorem, and also the matrix is like this. Hence, find the matrix represented. These are the total equations. While we are going to observing something, it is unable to understand like that different of the like problem is given. We misunderstand like that. But if we understand properly, we able to get that easily. Then how to get? By using the mention that it is a Cayley-Hamilton theorem. First of all, we need to find out what is the characteristic equations. Up to here, we get clearly without any facing the problem. That means S1 is a trace and S2 is the debt of the matrix, as we know that, and S2 is the minus and again S2 is 3 is the debt of the matrix. Up to here, without facing any problem, we can get that clearly the value of S1, S2, S3, and again here the values are S1 and S2, S3. We need to replace this the value, and again here they are asking to find out what is the inverse. The inverse is nothing but it is multiplied with A inverse on both sides. Therefore, we need to, after multiplication with A inverse on both sides, the matrix is reduced to A square minus 5A minus I, and again plus 37. A inverse is equal to 0. And after getting that, we need to get that A inverse, then easily, like as it is the previous problems, then we able to get no problem. Here the inverse of the matrix is nothing but 1 by 37 into this is the matrix. But our topic is here. Further, it is different. What it is different here? By using the Cayley-Hamilton theorem. That means here required to find out, they are asking to what is the value of this one. It is sometimes somebody are finding that A power 8 is nothing but if A into 8 times, and again A power 6 is the A power 7 is the 7 times of the matrix and A power 6 is the 6 times. But we should not follow that is a condition. Because of here they are asking to find out clearly by using the Cayley-Hamilton theorem. That how to find out? That means we need to recall whatever we got it, this is the characteristic equation. By using this one, we need to find out the required equation of this value. While we are going to observing here under this A power 8, from here to here, we need to take out common A power 5. Therefore, after take out common A power 5, the matrix is reduced to like this one. The rest of the values are no problem. Here, further, this value is equal to characteristic equation is satisfied. That means A power 5 into 0. That means that is total value is 0. But place A power 4 into from here. Again, while we are going to observing here it is what it is here. Here A is take out common. Therefore, after take out common A, it is equation is A into A cube minus 5A square minus 3A square, like this the terminology. While we are going to observing here A power 4, but characteristic equation is A cube. Already we take out common A. That means the rest of the value is A cube. And similarly, minus 5A cube. Again here take out common A. That means minus 5A square. That is a 5A square. Already existed the characteristic equation. Therefore, 5A square is clearly no problem. And minus 3A square. But it is A is required. But it is a minus 3A square. That split into like that two terminology. One side it is a minus A square and minus 2A square. Then only it is a minus 3A square. It is a whatever it is required. But here already take out common A. That means LHS side in that replace, that is a value, that is minus A. And again the rest of the values you put in the remaining term is the right side, that is a minus 2A square is the value. And further that 37i. But we already take out common A. Therefore based upon that, that is a 41A. And here 41A, here take out that is also split into, because of we require that 37 is mandatory. That means 41A we need to divide like that with 37. The rest of the value is 4A. Therefore, the 41A is split into like that. That is a 37A and also 4A is the remaining part. Therefore, here take out common already it is from the first part. Therefore, that's 37 we can replace in the LHS side. Therefore, 37I. And rest of the value 4A that we need to replace in the right side of the part. Therefore, from here to here, the term will be, by already it is satisfied the characteristic equation. Therefore, the value is a into 0. And again, plus the remaining part is like this. And further, we need to simplify the simple value of, that is a 3a plus 4a minus 2a square. And again, here we need to compulsory it is a find that a square. And given the matrix is A and A2, we need to find out what is A square. Therefore, A square is finding that A into A. The value of A square is 3 into I plus 4 into, this is the given matrix, that A into the matrix of A inverse is equal to, that is the A square. And again, we need to multiply first one, and again the multiplication, all the values should be A. Therefore, the required final solution is, the LHC set is given, whatever they are asking this one, we need to find the value of, it is a matrix is like that. That means, it is clearly, we obtain the previous value is, this is the final, the equation of whatever it is given the lengthy problem. And similarly, like this is also a problem by using the Cayley-Hamilton theorem, find the inverse and also find the value of this one totally. Without understanding the previous problem, it is not possible. Based upon the previous some example, first we need to find out, verify the, find the what is the characteristic equation, and again find the A inverse according to the Cayley-Hamilton theorem. And by using the Cayley-Hamilton theorem, we find this is the total equations. Like this is also one different type of the problem, whereas in the like a previous example only. Like this is up to here, no problem. We need to find out S1 and also S2 and also S3. That values we can replace in the equation of the characteristic equations. And again, by using the Cayley-Hamilton theorem, it should be satisfied. That means we need to replace lambda is equal to A. But here also we need to find that A inverse. That means we need to find out the total, the third equation is multiplied with A inverse. To multiply, the total equation is multiplication with A inverse as per according to the working rule of the Cayley-Hamilton theorem. And after that simplification, we obtain that A inverse is equal to, this is the matrix. That is as per the previous example, easy to understand, easy to get that. But here we should not do that according to follow that A inverse is equal to adjacent of A by dt or Gauss-Jordan method. We need to avoid that two methods. Clearly, the problem is asking to find out by using the Cayley-Hamilton theorem. And after that, the rest of the equation we need to find out according to, we need to remember the majorly what is the characteristic equations, and based upon that here also we need to take out common all these problems. Like it is also like based upon the previous example, we need to follow the conditions. Yeah. And again here from the equation of that is a 3, we obtain the value of 0. And again A square, the remaining term it is totally 0. The remaining term is A square plus A plus I. And A square is the matrix, we obtain that A into A. We found it. And again A is the given matrix, I is the unit matrix, such that the corresponding the order of the 3, that is a given matrix. And again that based upon this one, again the first element and again the second element, first two, and second, and third. And rest of the values are also corresponding that places of the matrices. Then we need to addition and subtraction depend upon that. We obtain this is the equation of totally whatever they are asking to find the solutions. Like these are the like other example also. If we need to practice, verify the Cayley-Hamilton theorem, verify ourselves only. Yeah. Like it is also same the corresponding the characteristic equations. And again here also take out common A is outside. That is a minus 2A, no problem. And it is also we need to find out. 3 is also take out common. Because of that A square is again that existed. Then finally A plus 5i. A is the given matrix and I is also the unit matrix. Consider the 2 by 2 order of the given related, that 1 0 0 1. Then A plus 5 is the matrix is obtained to 6 4 and again 2A. Therefore it is the final solutions. And these are the problems we need to find out. Like any problem is given, we need to find out. That means in these sessions, like these are the verification of the Cayley-Hamilton theorem. that by using the Karski equations, and moreover based upon the applications under the Cayley-Hamilton theorem, like to finding the powers and finding the inverse of the matrices, and in the last two problems we've shown that clearly to different type of the problems by using the Cayley-Hamilton theorem. Like these are the under the Cayley-Hamilton theorem that verifications, and also moreover it is application part is clearly we are understood. I think, I hope that. And again, in the further other classes, we need to discuss the continuation, that is a diagonalization of a matrix. Okay. And again, up to here, just we need to discuss. And again, any doubts or any questions, please throw this link also. Okay. I hope everybody understood that properly. Okay. Better luck in the next session, that is the continuation of the diagonalization of the matrix. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.